We have been discussing about the photochemistry of 1,4-diene. We have already looked few examples of this. So today also we'll see the photochemistry of 1,4-diene. 1,4-diene undergo very interesting photo rearrangement, that is di-pi-methane rearrangement, to give vinyl cyclopropane as the product if it is an open chain. This rearrangement has been exploited by taking different example, because this generates cyclopropane ring. Construction of a 3-membered ring, that is a highly strained system, is very is a challenging problem, and in the different workers have used this rearrangement to synthesize, to look different examples to see the formation of this product. So say for example, so for the criteria for di-pi-methane rearrangement is we should have a 2 pi bond separated by a methylene group. So we see, say for example, we have a system like this. So this is the starting material, and when we have a system like this, we have to analyze very carefully what is the chromophore present in this molecule, because in the initially what we have mentioned that the photochemistry of an organic molecule depends upon the type of chromophore present in the molecule. Say for example, you have alkene, so it undergoes cis trans isomerization. If there are two the proper substituent at 6 orientation, say for example 2 phenyl groups in cis orientation, the like cis is still being, so there is a possibility of, in the presence of light, there is a possibility of 6 pi electron cyclization. So this is, if we look at this molecule very critically, we have a 1 pi bond as another pi bond of the benzene ring separated by a methylene group. So 2 pi bonds, 1 pi bond, another pi bond separated by a methylene group. So this is nicely set for the di-pi-methane rearrangement. Di-pi-methane rearrangement under photolytic condition. The first step is the excitation of one of the double bond. We can excite any of these, either this or benzene, the double bonds or pi bonds of benzene ring. But ultimately what is the main intermediate involved in di-pi-methane rearrangement is cyclopropyl 1,4 diradical. So we'll just directly go to the cyclopropyl. So generation of this 1,2 diradical, this will attack here. Then so ultimately at the end, whether we excite this double bond or this double bond, we are going to end up with this 1,4 cyclopropyl 1,4 diradical. Now this is the main intermediate in di-pi-methane rearrangement. Now there is a possibility of a ring opening of the cyclopropane ring by via the formation of the double bond. So this radical goes like this, say for example, and then if we open this is a new bond formation in the cyclopropane ring. If you open this, we go back to starting material. So in order to proceed for the product, we have to break the old bond, either this. So when this bond, a double bond, this will open up. So and then let us see, and if we make a double bond here, so let us write the product of this pH, and there is a radical here, and there is a radical already here. And then if we make a double bond here, and then this will open up. So this is say A, via the cleavage of this bond A, and this, say for example, this is B. So via the cleavage of B, we end up with retention of a benzene ring, and then of course this is the old, and then this, and then we have a new pH. We have a pH here, and this is a new radical here. This is the radical already. So this is going to these are the two intermediate which is formed through the cleavage of the cyclopropyl ring. Either bond A will give this cleavage of bond B through the formation of. So if you look at the stability of this here, preferential formation of the, because the, if we make a double bond here and cleave this is going to be preferred over this, because here we are going to retain the aromaticity of the benzene ring. So here the this will not take place. The formation of this will not, like, of course this is going to give another product. So if we see, the final product is this one. And if we combine this, we get a final product is this one. pH and pH. So this is going to be preferred over the formation of this, because this is so because the cleavage of this, the formation of double bond, this will be much preferred, because the aromaticity of benzene ring is going to be retained, and hence this will once again gets aromatized, benzene will form, and then there will be a formation of new 1,3 diradical, 1,3 diradical, which will combine to give this product. So this is as we have mentioned, that di-pi-methane rearrangement is a very good rearrangement, in the sense that out of the possibility of these two products, this product is formed exclusively because of the stability of the radical, stability of the generation of the ring, and so on and so forth. And that's why this is the main intermediate, and this main intermediate will lead to which pathway is going to be going to take place, whether path A, where the cleavage of this, where we have to get a dihydrocyclopropyl derivative which is unstable, and here we are going to get a benzene attached propyl product, and then this is really important, because we end up with a more stable, out of these two possible products, we end up with the one more stable and more reasonable product. And there is a reason behind the formation of this, because the benzene ring, which was the one of the double bond of benzene ring which was generated at a radical species, now it is going to once again retain this through the formation of the double bond. Now let us see the second example, another example here. This is another example. So as we have mentioned, that the photochemistry of I think we'll just put it in this one. So this is the starting material, and as we have been discussing, that the photochemistry of organic compound depend upon the type of chrome 4 present in the. If you look at this very carefully, this is a one pi bond and another pi bond separated by a methylene group. And that's why this is very nicely set to undergo di-pi-methane rearrangement under photolytic conditions. So in this 1,4-diene this is 1, 2, 3, 4, 1, 4 diene, and nicely 2 pi bonds are separated by a methylene group, nicely set for di-pi-methane rearrangements, and then the steps involved, and let us see the product form in this rearrangement. We just will go stepwise by generating a diradical in one of the, we can generate either here, we can, let us generate here, because this is there is a presence of a phenyl group is going to more stabilize. Of course, we can generate a diradical here as well, but whether we generate a diradical here or diradical here, we end up with the common intermediate after this is, so it is very difficult to say which double bond is going to be excited and which, but we can definitely say that the main intermediate involved is the cyclopropyl 1,3 diradical. So this is the cyclopropyl. So cyclopropyl 1, 2, 3, 4, 1, 4 diradical. 1, 2, 3, 4, 1, 2, 3, 4, 1, 4. Cyclopropyl 1, 4 diradical. 1, 2, 3, 4, or we can just number from 1, 2, 3, 4 from here. Diradical is the main intermediate. Now, now this is the, as we have mentioned that this is the main intermediate which involves, which leads to the product. Now we have the examples which we have discussed. The radical which is more stable is not going to form double bond. So next step is the formation of the double bond and the cleavage of the cyclopropyl bond ring. So say for example, this is a new bond, is the new bond form, and this is the old bond, say A and B. So there is a competition between the formation of a double bond here and cleavage of this, or formation of a double bond here and then cleavage of this. So is now this radical is adjacent to a phenyl group, and we know that any radical which is adjacent to a phenyl group is resonance stabilized. Say for example, this radical you have, we can it will resonance stabilize like this. So we can write different resonance, just writing this part only, just writing this part only to see the stabilization, or how the radical adjacent to the phenyl group is stabilized. So this form a double bond here, and then this is a radical here, and then a double bond, and then this will once again form going here. So we know that the delocalized structure can be represented in a double-headed arrow, and then we can so this will form double bond here, a radical here, and then this will again form like this. So ultimately, if we end up, we can write here as the radical is moving all the way in the benzene ring. So this radical is highly stabilized due to the presence of a phenyl group, and then is not going to form a double bond here. So this is a localized radical going to form double bond here, and then preferential cleavage of bond A takes place. Preferential cleavage of bond A. Preferential cleavage of bond A takes place. So we end up with a double bond here. So we'll get a double bond here, and of course one 6-member ring is here. The radical is already here. There is a radical here, and then there is a bonding between this, right? So, and then this is a radical here. Now this 1,3 diradical 1,3 diradical is 1,3 diradical is going to combine here to give a product like this. The phenyl group is a is 3-member ring. So this is a product which is formed in this particular case. So this is the starting material. This is a 2 pi bond separated by methylene group, nicely set for a di-pi-methane rearrangement under photolytic condition, and hence the steps involved are the 1,2 diradical, the cyclopropyl diradical, and then cleavage of cyclopropyl ring via the formation of double bond. So the radical adjacent to the phenyl group will not form the double bond because it is highly stabilized, and we can see here different resonating structure. Other radical which is localized going to form a double bond, a cleavage of the old this bond takes place to give this radical, and then this is the product, a major product which is formed during this photo rearrangement of this particular case. Now coming to next example, let us see is this one. So for example, if we have a starting material like this, this one is a phenyl group, is a methyl group, and then this is a starting material, and then we can see here. So if we analyze this starting material and the condition is photolytic, we have a 1 pi bond here, 1 pi bond, and another pi bond separated by a methylene group. So 2 pi bonds separated by methylene group is the basic requirement for the compound to undergo di-pi-methane rearrangement. So let us see the stepwise mechanism. So we'll just write the steps, different steps involved in the first excitation of the. We'll just excite this as we have already said that is very difficult to say which double bond is excited, but we can assume that this radical is this double bond is excited, generating a diradical here. We can excite this, but ultimately whether we excite this and generate a diradical here or excite this and generate diradical here, the main intermediate is going to be the same in both the cases, and then that is the cyclopropyl. This will attack here to form a cyclopropyl derived. So this is the cyclopropyl derived main intermediate cyclopropyl derived 1,4 diradical. 1,4 diradical. Now the name now this is the main intermediate which leads to the product, and then this will now there is a possibility of the formation of double bond and opening. This is the new bond, and then this will form a double bond here, and if we cleave this new bond, we go back to starting material. So in order to proceed the product, we have to cleave either this bond, say for example say A, or cleave this and then make a double bond here and cleave this B. So as we have mentioned, this radical is again adjacent to a phenyl group, and the ring radical which is adjacent to a phenyl group or a double bond, it is highly stable and delocalized due to resonance, so it is not going to form a double bond here, whereas this is a localized radical which has no such stabilizing factor as is this one, so this form a double bond, and then this will be, so this will not take place, this will take place, and the preferential cleavage of bond B. Preferential cleavage of bond B takes place, and then we end up with a this is a phenyl group as it is, there is no change in this one, and then we have a this is a methyl group, and then we this one, this has broken, and then this is the radical. So 1,3 diradical, 1,3 diradical, 1,3 diradical is formed, and now this will of course it is, there is a double bond, sorry, there is a double bond here, and now this will combine to give a product like this. This is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and then 3. And then so this is a very interesting product. We started with the monocyclic system, monocyclic 6-membered ring. At the end of it, we take a bicyclic 5 plus 3 ring system. It's a very interesting rearrangement. So this di-pi-methane rearrangement, if we have a nicely set 2 pi bonds separated by methylene group, we end up with a synthetically important from open chain going to a cyclopropyl product, and if you from the monocyclic system, we end up with a bicyclic system with a 3-member ring. The construction of 3-member ring is a very important from synthetic point of view for an organic chemist, because this cyclopropane ring construction is not very easy due to the highly screened ring system, and hence it has drive a lot of attention for the scientists, for the different workers. Now coming to the next one, this is also, there is again an example of di-pi-methane rearrangement. So you have one double bond, another double bond, and there is a phenyl group, and then its condition is photolytic. Now if you look at this very carefully, we have again one pi bond, another pi bond, and of course there is a third pi exocyclic double bond is. But if we consider these two, and then there is these 2 pi bonds separated by a methylene group. So 2 pi bonds separated by a methylene group. So this part can participate in di-pi-methane rearrangement. This part can involve in the rearrangement. So we can just excite, we can go and look for what is the product at the end of the photolysis of this particular compound, and then if we just look at the product for this starting material, we can see the excitation. So these both are, so we can either excite this or and then or excite this, or we cannot say which bond is exciting, but at the end what we end up with the main intermediate. Main intermediate is cyclopropyl. This is the main intermediate which is formed at the involving di-pi-methane rearrangement. There is a new bond formation, a cyclopropyl ring, a 3-membered ring, is a 5-membered ring, and now this will lead to the product. So here there is no, either we make a double bond here and cleave this, or make a double bond here and cleave this. The product is what product which we get is the same. So let us cleave one of these, because this, as far as the stability of this diradical is concerned, this is stabilized this side as well as this. So as far as the stability is concerned, both the radicals are same way is stabilized, and hence there is no important factor. So let us form a double bond here. a double bond here, and then if we cleave, this is a new bond, cleave big, this one we go back to starting material. So if we cleave this bond, say for example A, then we end up with a and then sorry, this is, we get this one, and then this one, and then this double bond. So this is the entire the new radical 1 2 3 1 3 diradical is the intermediate form, and then this will combine to give the product like this. So this is the product, and then we can see this is a 1 6-member ring going to end up with 5 and 3. It's highly interesting. And if we make a double bond here, then it will be, this double bond will be here, and the cyclopropane will be other side. So as far as the product is concerned, either can make a double bond here, a cyclopropane this side, or other way around is the same. So this is a very interesting, because again from a monocyclic system, monocyclic 6-membered system, we are going to end up with a bicyclic 5 plus 3 product, and very nice, nicely set for rearrangement of these products, and hence it is a very interesting rearrangement for the so this is all for today, and then we'll continue this soon. Thank you very much.